This instructional video illustrates the process of analyzing the stress levels in compound cylinders.
What are compound cylinders?
In mechanical engineering, a compound cylinder is a cylinder that is made up of two or more cylinders concentrically fitted together. The shrinkage produces residual stress distribution within the walls of the cylinders, which improves the cylinder behavior against the working pressure.
Compound cylinders are used in a variety of applications, such as hydraulic presses, forging presses, power plants, gas storages, chemical and nuclear plants.
The main advantage of using a compound cylinder is that it can withstand higher pressures than a single cylinder of the same material. This is because the residual stresses produced by the shrinkage help to counteract the stresses caused by the internal pressure.
Another advantage of compound cylinders is that they can be made lighter than single cylinders of the same strength. This is because the inner cylinder can be made of a weaker material, as it is not subjected to as much stress.
The main disadvantage of compound cylinders is that they are more difficult to manufacture than single cylinders. This is because the cylinders must be shrunk together precisely, and any misalignment can lead to stress concentrations.
Let us see how to find out the stresses induced in a compound cylinder. For example, consider a compound cylinder made of two concentric cylinders made of the same material.
The inner and the outer radii of the compound cylinder are capital R1 and capital R3 respectively. The inner radius of the outer cylinder and the outer radius of the inner cylinder are the same, and it is taken as R2. We call this as interface radius. Because the two cylinders are fitted with a tight fit, a pressure, called as P interface, is induced at the interface. This pressure compresses the inner cylinder whereas it expands the outer cylinder. You can observe how the interface pressure applies on the surfaces of the two cylinders in the diagrams given here. To examine the stresses, we can analyze the two cylinders individually, one experiencing internal pressure exclusively, and the other subjected solely to external pressure. Subsequently, we observe the initial stress distribution solely considering the pressure at the interface, without the cylinder being externally pressurized yet.
For the analysis of stresses, we use the Lahm's equations. Lahm's equations gives the radial and hoop stresses on the cylinder wall at radius r as given below. If you are not familiar with the graphical representation of Lahm's equations, watch the video on thin and thick-walled cylinder theory. The link is available in the description.
First, draw the vertical stress axis and horizontal 1 over r squared axis. Mark 1 over r squared values on the horizontal axis, and draw corresponding vertical lines for R1, R2, and R3 on both radial stress and hoop stress sides. Mark the interface pressure, P int, as a compressive radial stress. Also mark the radial stresses at the inner and the outer surfaces as 0. Join the stress points, marked for the inner cylinder, and extend the line to the hoop stress side. Similarly, join the stress points marked for the outer cylinder, and extend the line to the hoop stress side. Corresponding values of hoop stresses for the inner and the outer cylinders are represented by AB and CD respectively. In this case, the inner surface of the inside cylinder exhibits the highest compressive hoop stress. As a result, when the pressure is applied to the cylinder, this stress diminishes gradually before the cylinder undergoes tensile stress. This means that the cylinder can withstand higher pressure than that of a single cylinder that is initially not stressed. Now, we will examine the process of determining the stresses in the two cylinders when the compound cylinder is subjected to pressurization. There are two cases we need to consider. Number 1, cylinders are made of the same material, and number 2, cylinders are made of two different materials. Initially, we consider the cylinders composed of identical materials. You can see here the initial stresses, when there is no applied pressure. The stresses are only due to the interface pressure created due to the tight fit between the two cylinders. Suppose we apply a pressure of P inside the cylinder. Then, we see how to estimate the new stress levels in the two cylinders. Given that both cylinders are constructed from the same material, we can consider the combined structure of the two cylinders as a single unit. It is important to note that in this scenario, the diametral deformation or strain at the interface radius is the same for both the cylinders. Therefore, mark the applied internal pressure, P, on the line of inner radius as a compressive radial stress. Also, mark the zero stress at the outer surface. Next, join the 2 points, and extend the line to the hoop stress side. This line gives the stresses caused solely due to the applied pressure. To obtain the resultant stresses at a given point, you need to add initial stress, and the stress due to applied pressure. For example, if you want to find the resultant hoop stress at the inner surface, add AF and EF. Since AF is negative, the resultant stress is EF minus AF. This gives a small tensile stress, as seen in the diagram. Let's now consider a compound cylinder made of different materials.
Due to discrepancies in the mechanical properties of its constituent materials, a compound cylinder composed of different materials cannot be regarded as a unified cylinder for stress analysis under pressure, as done for a compound cylinder made of the same material.
Under these circumstances, it is necessary to treat each individual cylinder separately, and determine the new interface pressure upon the application of pressure. Thus, for a known internal pressure P, which sets up a common interface pressure, P(I)N(T), the solution takes the form shown next. First, set up the axes for stress, and 1/r squared. Also, draw the vertical lines to represent 3 surfaces of the cylinder. Mark the applied pressure P as a compressive radial stress on the inner surface. Next, mark a assumed new interface pressure P(int) as a compressive radial stress. The interface pressure should be such that it satisfies the requirement of equal circumferential strain in the two cylinders at the common interface radius. We can write an equation for the interface pressure, in terms of hoop stresses of the cylinders at the interface radius, and the material properties, which can be used along with this diagram, to find the stresses in the cylinder walls. We will look at this equation shortly. Meanwhile, we continue to construct the stress lines here. Draw the line joining these 2 points and extend it to the hoop stress side. For the outer cylinder, draw the line joining the point for interface pressure, and the zero stress point on the outer surface. In the graph, the line AB represents the hoop stresses in the outer cylinder, and the line CD represents the hoop stresses in the inner cylinder. Now we can calculate the stress values any point, with the use of trigonometry, and the equation that fulfills the requirement of equal strains at the interface radius applicable for the two cylinders. Let us now look at how to find values of stresses of the compound cylinder composed of 2 different materials, when subjected to an internal pressure. One of the equations we can use is that equal circumferential strains at the interface due to applied internal pressure. For this we can use the equation given here. The other equations have to be derived using the plot of stress lines we have already constructed. We require 3 more equations, as we have 4 unknowns, namely interface pressure, 2 hoop stress values at the interface, each for 2 cylinders, and the value of x in the plot. The x is the intercept on the horizontal axis for the stress line corresponding to the inner cylinder. We can write 3 relationships referring to the stress lines in the diagram. First, consider the triangles DFI and ILM. From these 2 triangles we can obtain a relationship between x, applied pressure, P, and the hoop stress at the interface radius for the inner cylinder, sigma, Hi. Next, consider the triangles AFJ and JKN. From these two triangles we can obtain a relationship between interface pressure due to applied internal pressure and interface hoop stress for the outer cylinder, sigma, h, o. Now consider the triangles ILM and IKN. From these two triangles we can obtain a relationship between interface pressure due to applied internal pressure and the value for x. Now, we have four equations to find out all unknown values as given here. The unknown values you may need to find out for a given applied pressure P are interface pressure due to the applied pressure and the hoop stresses at the interface. Note that these are the additional stresses caused due to the applied internal pressure. The net stress levels and the interface pressure have to be determined by adding the initial stresses due to the shrinkage.